Hello, my name's Geoff Hyett and I'm a lecturer at the University of Leeds. Today's question is, explain the reasons for the different methods used in extracting metals. Well, in the extraction of metals, as with any industrial process, there are a number of factors affecting the choice of method, including of course economic ones. It makes sense to use the cheapest method available. But the principal factors that have to be considered are the chemical ones. Most metals, apart from a few noble metals like gold or platinum, are found in ores, bound to either oxygen or sulfur in positive oxidation states, generally between +1 and +4. In order to liberate the metal, you have to carry out a chemical reaction to separate the metal from the oxide or sulfide, while at the same time reducing its oxidation state to 0 to give it in its simple elemental form. So metal extraction reactions are also redox reactions, where we wish to reduce the metal, that is to donate electrons to it or lower its oxidation state. To do this, a reducing agent must be used, and the choice of reducing agent depends upon the stability of the ore. To illustrate this principle, we'll look at three examples: the extraction of iron, titanium and aluminium. These metals each have very different methods of extraction due to their different chemistries, and this is reflected in their cost. These of course vary with market forces, but the current values are about 30 pence for a kilogram of iron, £1.50 for aluminium and £16 a kilo for titanium. This is a 50-fold difference between the cheapest and most expensive metal. By considering each of their extractions in detail, we'll be able to explain this difference and why the chemistry of the systems dictates the method used. Let's turn to my first example and the cheapest metal, iron. This is extracted from an oxide ore, iron 3 oxide, in which the iron is relatively weakly bound compared to our other examples. It can be reduced by carbon monoxide to metallic iron, with carbon dioxide as the byproduct, as seen in this equation. The extraction is carried out in a blast furnace, where the ore is combined with air and elemental carbon in the form of coal, coke or charcoal. The ore and carbon source are loaded into the top of the furnace, while the air is pumped or blasted, hence the name, into the bottom of the furnace. Inside the furnace, the carbon and oxygen combine in an exothermic reaction, which provides the heat needed for the iron oxide reduction, which must be carried out at high temperatures. Under these conditions, the main product of the carbon and oxygen reaction is not carbon dioxide, but carbon monoxide. So this reaction provides not only the necessary heat, but also the reducing agent which reacts with the iron oxide ore. Carbon is a relatively cheap reducing agent, iron ores are abundant and air is for all practical purposes free. So this process can be run continuously using these inexpensive reagents with this simple furnace design, and this makes iron an inexpensive and widely used engineering metal, and the cheapest of our examples at 30 pence a kilogram. If we now consider our other examples, titanium and aluminium, these are both also found as oxide ores, and the extracted metal have both better strength to weight ratios and superior corrosion resistance than iron, and yet are much less widely used because of their greater expense, roughly 5 and 50 times more expensive than iron respectively. The principal reason for this greater expense is not that their ores are rarer or more difficult to obtain. Both titanium oxide and aluminium oxide are relatively abundant and inexpensive. They're more expensive because they cannot be extracted from these ores using a simpler method or as cheap a reducing agent as coal. Both aluminium and titanium are much more strongly bound to oxygen in their ores, and so cannot be reduced by carbon monoxide. Other cheap reducing agents like hydrogen or carbon itself are also not strong enough to extract titanium or aluminium. So to extract these metals, alternative strategies and more powerful reducing agents have to be used. The principal ore for titanium metal is titanium dioxide. In the first step of the extraction, it's reacted with carbon and chlorine to form titanium tetrachloride. This is done because titanium metal is significantly weakened by the presence of any oxygen or carbon impurities. So it's first converted to titanium tetrachloride, which is a liquid with a relatively low boiling point of 136 degrees Celsius. This can then be purified by distillation to remove any carbon or oxygen. However, this still leaves titanium in the +4 oxidation state and strongly bound to chlorine rather than oxygen. So although we've eliminated the risk of any weakening impurities, we are still no closer to the reduction of the metal. So a final reduction step is then carried out by reaction with either sodium or magnesium metal, both of which are strong reducing agents. And this is conducted in a batch reaction using an inert argon atmosphere to exclude oxygen, which of course would both weaken the titanium and react with the reducing metal. So this is a multiple stage batch process using other purified reagents like chlorine and argon gas and sodium or magnesium metal. All of these themselves require expensive processing to produce. All of these factors, dictated by the chemistry of titanium extraction, combine to make it the most expensive of my three examples. My final example is aluminium. Now, like titanium, it too is strongly bound to its oxide ore and cannot be reduced by carbon or carbon monoxide. It could be reduced chemically by using a strong reducing agent like sodium or magnesium, but this would cause it to be extremely expensive. However, for aluminium, a more economic alternative exists. To extract a metal, it needs to be reduced, and reduction is a gain of electrons. So the most direct route is to do this using electricity. As such, aluminium can be extracted through an electrolytic process, the use of an electrical current to drive an otherwise unfavourable reaction of free-moving ions in a liquid phase. The electrolytic extraction of metals, which is also the source of the sodium and magnesium used to extract titanium, has the advantage that the reducing power of the electrical current is directly proportional to its voltage. So it's very easy to tune the reducing ability to the specific metal in question. There are of course disadvantages, otherwise all metals would be extracted using electrolysis. Firstly, it's generally cheaper to reduce directly with carbon or carbon-based reagents where possible. And secondly, you need free-moving ions, so the ore must be melted or dissolved, which would often require prohibitively high temperatures. Indeed, the melting temperature of aluminium oxide is in excess of 2000 degrees Celsius, and it's too high for economic extraction. So instead, it has to be dissolved in molten cryolite, with the current being passed through carbon electrodes. Cryolite is an aluminium mineral with a formula of Na3Alf6, of which only one major deposit has been found, in Greenland, but this has now been depleted so that all cryolite used in aluminium extraction is in fact produced artificially. Cryolite melts at 1020 degrees Celsius, and aluminium oxide will dissolve in this. Although this temperature is still high, it's much lower than trying to directly melt the alumina and makes the process economic. Once dissolved in the cryolite, the aluminium oxide forms aluminium 3+ ions, which are attracted towards and reduced by a transfer of electrons at the cathode. The molten aluminium which is formed then collects at the bottom of the cell where it can be tapped off. A voltage of only about 4.5 volts is used, which seems low, but a very large current is needed, such that every 1 kilogram of aluminium produced needs about 15 kilowatt hours of electricity. So as we've seen with these three examples of titanium, iron and aluminium, all have very different methods for their extraction. Iron by simple combination with carbon and air, aluminium by using electrolysis in molten cryolite, and titanium with its multi-stage batch process and need for a number of other purified and expensive reagents. Yet all are driven by the same motivation, the need to find the cheapest route that satisfies the chemical requirements of a strong enough reducing agent to separate the metal from the ore and leave it without any detrimental impurities.